We tend to think of the pyramids as finished history, stone relics baking in the Egyptian sun, whose stories were told millennia ago. But right now, these structures are acting as active frontiers for modern science. This graphic shows a massive 30-meter-long void recently detected inside the Great Pyramid of Khufu, and it isn't an isolated anomaly. In 2026, researchers confirmed a similar pair of hidden cavities right behind the eastern face of the nearby Menkaure Pyramid. To find these spaces without moving a single stone, physicists are using cosmic ray muons. These are high-energy particles raining down from the atmosphere that can pass through solid matter. By measuring how these particles accumulate, researchers can essentially take an X-ray of the pyramid. These scans are finally giving us the data to address a logistical math problem that has stumped engineers for centuries. The Great Pyramid is composed of 2.3 million individual stone blocks, totaling roughly 6 million tons of material. And according to historical records, the entire project was completed in just 20 years. When you run those numbers, the deadline imposes a staggering physical reality. Assuming a 10-hour workday, the builders had to quarry, transport, and perfectly place one multi-ton block every 2 to 3 minutes. And they had to maintain that exact pace without interruption for 2 solid decades. That brutal, unforgiving math is exactly why we spent centuries inventing theories about alien architects or armies of millions of slaves. The true logistics seemed impossible. But today, an alliance of particle physicists, archaeologists, and mathematicians are piecing together the physical evidence to show exactly how human organization accomplished it. The precision at Giza didn't appear out of nowhere. Generations earlier, Pharaoh Sneferu commissioned this structure at Dahshur, now known as the Bent Pyramid. It served as a massive, very public prototype. About halfway through construction, the builders realized their steep 54-degree slope was structurally unstable. The monument was literally starting to collapse under its own colossal weight. To save the project, the engineers made an abrupt mid-course correction, finishing the top half at a much safer 43-degree angle. The flawless geometry we see later at Giza is the direct result of that near catastrophe. The Egyptians learned structural physics through generational trial, error, and highly visible failures. To understand who actually applied those physics, archaeologist Mark Lehner spent decades digging south of the Giza Plateau, looking for the specific people who built the Great Pyramid. He uncovered a massive urban center. The site contains blocks of long, sophisticated galleries designed specifically to house and manage a labor force of several thousand people at a time. The trash pits outside these galleries are filled with forensic evidence. Lehner's team found industrial-scale bakeries and thousands of bones from fish and young male cattle. Whoever lived here was eating a highly caloric, protein-rich diet, food that was incredibly expensive in the ancient world. The people eating that food were fulfilling a civic obligation the Egyptians called bak. It was a system where citizens owed a portion of their labor to the state, operating entirely separately from the modern concept of slavery. The archaeological record proves these builders were a privileged, well-fed class of skilled citizens. They were structured into highly organized labor gangs on a rotating basis, bringing specialized knowledge to the plateau, and then taking those wages and skills back to their villages. But even a well-fed workforce has to obey the laws of physics. A recent engineering feasibility analysis by Cadence AI ran the physical constraints of the 3-minute block deadline and proved mathematically that no single massive external ramp could deliver stones fast enough to hit the target. However, the transport required specific mechanical hacks. To move blocks from the quarries, workers poured water over sand directly in front of their wooden sledges. This created capillary bridges between the sand grains, effectively halving the ground friction and allowing a constant flow of heavy material to the base. The Grand Gallery's exact slope and geometry allowed it to function as a mechanical component, an active internal machine integrated into the masonry to assist the builders. This diagram illustrates how a massive granite sledge could be loaded into the Grand Gallery. Sliding down the 26.5-degree slope, the descending sledge acted as a giant counterweight, pulling a rope system that hoisted fresh stone blocks up a central vertical shaft. By leveraging gravity along that specific incline, The system provided enough mechanical advantage to lift blocks weighing up to 10 tons. Running on an 11-minute reset cycle, a single internal pulley system could execute 50 heavy lifts a day. The builders didn't rely on one impossible method. They combined wet sand transport, short external ramps, and internal counterweights into an adaptable, multi-method production line. It was an exercise in extreme efficiency. This bar chart visualizes the total energy budget for the entire project. Factoring in localized engineering hacks and simple machines, the total caloric requirement sits comfortably within the capacity of 20,000 to 30,000 workers over 2 decades. That math brings us right back to the voids discovered by the muons. In 2026, researchers are preparing to unveil exactly what sits behind a sealed door at the end of that 30-meter corridor, hidden inside Khufu. These monuments function today as active laboratories, yielding fresh data on how a Bronze Age culture mastered the interactions of scale, mass, and time. The pyramids stand as the physical result of shared belief and relentless iteration, proving the capacity of collective human engineering.